we resume after the breaks, and we've got YAndrew explain to us about exploring self-regulation and transport barrier.
Thank you very much. So, is that better? It's not echoing. Okay. My voice is worse than usual, so can you let me know at the back if you can hear me? Yes, okay, great. I'll try and stay close to the microphone. So yeah, today's talk is on exploring the self-regulation in the edge transport barrier. I would like to thank my collaborators. As usual, this kind of work isn't possible without a large team of helpers and contributors. So an outline of the talk, I'll start with an introduction to plasma confinement studies. I was asked to cover this pet project of mine over the past few years, and this is the dependence of the L to H transition power threshold on the magnetic null point configuration. And then go on to show you a more recent experiment that we've done on mass use vertical tokamak, the relative density perpendicular velocity fluctuations, how they evolve, some information geometry analysis on those results, and then conclusions. Okay, so here we have a ploidal cross-section of a tokamak. We're going to be using a lot throughout this talk radial profiles, and the radius is often taken here at the magnetic midplane. And here we have a schematic of plasma pressure against the normalized plasma radius. So obviously one at the separatrix, then we move off into the scrape-off layer. So it's well known that as the plasma input power is applied, if it reaches a threshold value of input power, an edge transport barrier spontaneously forms. This edge transport barrier is a very thin layer just within the separatrix, and is characterized by reduced turbulence. That reduced turbulence leads to improved confinement because we have less cross-field turbulent transport into the scrape-off layer. So typical L mode profile here is smooth from the plasma core out into the scrape-off layer, and then on the formation of this ETB, the edge transport barrier, this very thin layer, we develop these steep pressure profiles within the separatrix, which leads to this propping up, if you like, of the plasma pressure and the so-called H mode. So the L mode, the low confinement mode, is characterized by removal of heat and particles from the core plasma, generally detrimental, although it has some advantages, detrimental to plasma performance. So on the discovery of the H mode, the key benefit from that is access to much higher core plasma pressures, which is obviously useful for accessing fusion conditions. I've shown here so this is the mass U cross-section, and this is a double null configuration that we use for the experiment I'm going to come back to later. And then on the left here, we have two graphs. So we have this is the electron density profile. These were measured using Thomson scattering, the electron temperature profile. This color scheme that I've shown here, so the purples are in the L mode. You can actually start to see the density pedestal, the steep gradient of density pedestal beginning to form actually within the L mode phase. And you can see it's very smooth temperature profile here. So this is real data. It's an example shot that we've used to study. And then as we go into the pink and orange, which is after the formation of the transport barrier, which so the H mode colors we'll be using here, you can see the much steeper density profiles forming, so characteristic of the H mode. And a little bit in the temperature. The shots that we have studied are very close to the transition, so we don't tend to see very steep temperature profiles. Those tend to come as the H mode evolves, you apply more heating. So this is very characteristic of the type of shots that we look at. So just a note on a power threshold, that's generally calculated from the total input power into the plasma, and then we subtract the rate of change of the core plasma energy. And some studies as well, if they have the 2D reconstruction, they can also calculate the radiated power from the bulk plasma. So what they're interested in here is really how much power reaches the edge region. So that's the metric of interest. Okay. So it has its problems, elms and other problems, but it remains an interesting mode of operation for future devices. So we have talked about this a lot in this meeting, but if I consider three kind of key contributing mechanisms to the formation of the ETBs, this is a simple approach at this stage. So we know that, for example, turbulence in the L mode, pressure gradients can drive turbulence. Turbulence can drive the formation of the zonal flows, which we've seen really lovely examples of in computational work over the week. The zonal flows, localized flows, can themselves begin to suppress turbulence by breaking up the eddies due to the shearing action. Once the turbulence starts to become suppressed by the zonal flows, the pressure gradient begins to increase. Once the pressure gradient begins to increase, the formation of the radioelectric field structure strengthens, deepens, then we end up with these regions of E cross B flow, which can in turn, the shear E cross B flow can start to suppress the turbulence even more, and you end up with a building up of the ETB. So here is an example of some earlier work that we did on D3D. So this is an example of a sharp transition, and we have an example of a dithering transition on the right. So if we look at this sharp transition, so we've overplotted here in blue, this is the radioelectric field measurement from the charge exchange diagnostic. So in the dotted lines is the L mode profile, and the solid line shows you the H mode profile. So you can see very clearly the formation of this steep E region. And these gradients in the E region, or the ER well, as it's famously known, drive the shear flow velocity in the H mode for suppressing turbulence. And then in red, we've overplotted the perpendicular velocity measurements in the colloidal plane from the DBS. And you can see it reproduces the location of the ER well. So this is essentially a V perp well, and it also has these regions of shared velocity. Okay. So the power threshold to access H mode has been, we know it's very sensitive to the magnetic null point. Just the fact that H mode was discovered after a magnetic diverter was introduced on Aztecs is the biggest clue that it has a contribution to the formation of the ETB. I think that's kind of an obvious statement. So it's been well known there's a sensitivity there. In the 80s, and definitely in the 90s, more attention started to be given to the topology of the magnetic diverter and how that influenced the access to the H mode. So there's a lot of work on the direction of the B grad B ion flow relative to the magnetic diverter, for example, and actually attention to the location of the magnetic null point and how that affects access to H mode. So some points here on the thinking behind that. As soon as you introduce a magnetic null point, that vanishing magnetic field in the vicinity of it leads to an ion velocity loss cone. So you have essentially exit current at the magnetic null point. The plasma always acts to restore ambipolar flow through the formation of electric field, the exit current to and so we come back to this equilibrium situation with the presence of the electric field structure and ambipolar flow. So the magnetic null point itself can contribute to that formation of the radioelectric field. Some other thoughts on that. So we saw in the first talk the beautiful flux expansion that happens in the vicinity of the magnetic null. So certainly we understand that magnetic helicity and magnetic shear, we think, are contributing factors to the formation of the ETB. And this is a really important area that we're very interested in. There's been lots of work on that. We're very limited in studying that by the diagnostics available, but I've put some references here in case you'd like to have a look. We also know that neutral fueling through the magnetic X point is significant. So that neutral fueling through the magnetic X point can lead to charge exchange processes, which have an effect on momentum deposition and also on the local conditions at the X point, such as radiation and temperature effects. And then the magnetic diverter topology, the magnetic null point location, can affect the diverter recycling patterns, which in turn can influence X point fueling and in turn influence the edge plasma. So these are things that we know. We are limited by the diagnostics that are able to measure in the vicinity of the X point to try and understand further what's actually going on. Okay, so first experiment. So we have here 2004. I published this work, so we've been working on it for quite a while. So these were so work had gone on actually before I did these experiments, but these were the first experiments to actually try and disentangle the effects of triangularity close to the X point and actually moving the X point location. So here we actually moved the X point location vertically. And what I was interested in was the vicinity of the X point to this septum that was on the joint European torus, the jet torus, and we ran the experiments again without the septum. So here we have this replacement plate. Essentially what we found, is the vertical distance of the X point relative to the septum, which is why we have these negative values. But essentially over this region of about 24 centimeters, what we found was that the power threshold was significantly affected. So you could control the power threshold and the power requirement for accessing the HMO significantly. So we have a factor of 4 to 5 by varying the X point vertical location. And for these particular shots, the strike points remained on the horizontal target. The triangularity was kept the same. We tried to do some of these scans at constant density to understand what was going on. And then more recently, we returned to this to do some really great experiments with 3D, with Lothar, to look at. So here, actually, we were using this upper magnetic null, and we were looking at the difference between this. You can see the outer strike point is in this small angle slot diverter, and then we moved to the horizontal target. So there was a few things we were looking at there. The effect of the outer leg length, which resulted essentially in a vertical distance of the X point. And we were also looking at the effect of, this is a more closed diverter, so the effect of neutral recycling on the power threshold. So what we found were similar results to those that we saw on JET, with these very low values of X point height. And then when we moved far beyond that through to this much further away region, which was actually the other diverter, made it a bit more difficult to study, but we see this opposite trend. So interesting results. There's quite a lot to try and disentangle there. We did these scans at 3 different densities. So you can see that the most sensitive dependence was at the mid and high density, so the orange and the red. This was for both sets of data. And then at the lowest density that we explored, there wasn't much. So in the blue, there wasn't much dependence there on the Z X point height. And then I just wanted to highlight these really interesting experiments that we run on NSTX by Devin Battaglia. So this was published in 2013. And there, the thinking behind it was that the X point radial location would also be very sensitive. The velocity loss count was very sensitive to the X point radial location. So, and they ran these experiments. So you can see here it goes from the blue to the red and the other way around. So we have a distance of about 17 centimeters change, and these were done at the densities here. You can see they tried to keep the pedestal density constant. It was a good attempt to keep some of the values constant, and we tried to separate out here high recycling conditions versus low recycling diverter conditions by using a lithium coating in the diverter. So the key outcomes from that work was that the power threshold increased significantly at the smaller radial location of the X point and under higher diverter recycling conditions. Again, this was attributed to the the radioelectric field impact of this. And there's questions here remain on the influence of the magnetic shear. I mean, you can see that the triangularity is changing very much in changing that radial electric field. And even though there was a pump diverter, I do have questions here on neutral flux and recycling patterns and how those would influence the conditions at the X point. And now I'm going to attempt to report on this very interesting and more recent study by Guillaume and Yannick on the introduction of a cold spot. So I'm highlighting this because it really changed the way that I was thinking about approaching these experiments. So for me, this is very important work. And so, having worked on it for a long time, this was kind of a very new idea on how all of this works. I'll try and summarize, but they're here to explain more clearly. There were essentially three cases, and two of the cases used, this was calculated using the Gisela gyrokinetic code, and we have a symmetric colloidal plasma. So case 2 and case 3 had colloidal symmetry. Case 1 introduced a limiter, essentially here. And what the limiter does was introduce a cold spot. So it breaks up the colloidal symmetry. And then what they found was that the formation of this organized boundary within the separatrix, so this H-mode-like conditions, was only possible on the introduction of this cold spot through the limiter. So highlighting the importance of the interface between plasma, and in this case, it's a material boundary. It could be, and the paper notes, it could be applicable absolutely to a magnetic null. The point here is that the neutrals provide power dissipation in the vicinity of the null and provide this cold spot. Turbulent eddy is born with this cold spot, then spread out due to pressure differences and advection. So we have turbulence spreading from the X point outwards, and then self-organization into a turbulent boundary with zonal flows and the formation of the H mode just within the separatrix. Okay, so we ran an experiment on mass U, and these are some of the experimental parameters. It's key to note that we use the SuperX diverter configuration. So you can see here that the stroke point is far away from the confined plasma and from the magnetic null. Here are some general parameters for this shot, so the time traces. So we used a bit of a trick to delay the access to the H mode by using gas puffing on the low field side to delay the onset along with the power input using one of the MBIs. We then switched to this gas puff. You can see the gas puff on the high field side, but we wanted to drop the gas puff. So that allowed us to drop the core plasma density, which I'm showing here. So we were trying to access the H mode by dropping the core plasma density. It kind of stabilized, we're sort of increasing that at this point. Then you start to see we entered this kind of phase of dithers. This is the core plasma density being affected. And then we entered these more cyclic dithers in this point. So this was an interesting shot for us because it provides these cyclic ETB formation and collapse. So it essentially slows down the alter-age transition, given the temporal the limitations and the temporal diagnosis that we have, that we can actually study the interactions there. So here's a close-up of the phase that we were interested in for this shot. So these shots, I have to disclaimers that these shots are sawtoothing. In fact, I think all the shots that we've had so far on mass-U are sawtoothing, and the dithers and the ETB formation is often triggered by the sawtooth delivering a local pulse of edge plasma. We haven't been able to get away from that. I'm not presenting any power threshold measurements today for that reason. More to come on this. So pre-dithering phase, essentially the power is constant over this time. The density is changing, it's actually increasing, dropped a little bit here. And then you can see in this phase, we enter these very regular cycles of H mode-like, L mode-like. This is the alpha signal. You can see when it drops, it's a clear indication that the transport barrier has formed. Particles to the diverted targets drop, and then we're in the H mode-like phase, and then it breaks down, and we have these cycles. So inspired by that work, it made me, and I wouldn't have done this, it made me go and look at these 2D emissivity plots. So this is the work by Fabio Federici on MassU, who did this wonderful work on this diagnostic to study mass with Bruce Lipschultz. So that was the purpose of developing this diagnostic. And you can see these wonderful 2D mapping of the superextroverted and the X-point region. So we went back and had a look at this, and what we found is that in the L mode phase, kind of proper, the emissivity is distributed along the inner glass closed block surface and along the outer diverter leg. And then in the pre-dithering phase, you can see that the radiation starts to move towards the X point. And then what we found is that the beginning of the dithering phase coincides with the localization of the radiation at the X point. 10 minutes, thank you. And so these are so essentially we've divided the region into an inner separatrix, inner core, if you like, and around here, approximately around there, outer core, and then the X point region is sort of a circle around here, and that's what we've plotted as the time trace in the bottom graph. So the transition happens at 6:05, 6:03, and then you can see it kind of coincides with the peaking of the X point radiation localization of it, and that continues through the dithering phase. So more to come on this. We have, so I think we have about 12 or 13 shots, a small database of shots on MassU. Out of the 11 show this kind of behavior in L to H transition. So there's much more work to go to figure out what's going on. We think it could contribute to be part of the picture of what's happening there. The back transition, so the H to L transition, is less obvious. That we don't have a clear picture yet, so possibly a different mechanism. Okay, so Lothar very nicely described the Doppler backscattering system earlier week, so I'm not going to go into details of that. It's very similar in how the measurements are made. I think it's built by the same UCLA team, so we have 8 frequencies that are used to probe the plasma. You have the indication of the location here. So this is the region, the normalized radius region that it tends to cover across the 8 channels, and so very much like focusing on the edge into the scrape-off layer a little bit. The relative density fluctuations and the perpendicular velocity is what we measure, what we're interested in from this diagnostic. So what we've done is to calculate the probability density functions of the 2 variables of interest. For the relative density fluctuations, we've used the time resolution. We've used 0.5 milliseconds to construct the PDFs, and typically it has thousands of points, whereas we 1 millisecond for the V perpendicular PDFs, and then that allows us to calculate the statistical quantities from that, such as the mean, the standard deviation, skewness, and kurtosis. Okay, so I've considered here, it's not showing up very well here, but between the blue and the yellow line, is what we're considering for one of the cycles in going from the L mode through to the H mode. So again, we're using those similar color patterns. So in purple, we have here the L mode phase distribution. So these are the relative density fluctuations, PDFs going from channel 1, which is at the separatrix into the scrape-off layer, through to channel 6, which is more into the core of the plasma. And so what you can see if we look at the tail, so in the L mode density, the distributions are very wide, very flat, and you can start to see prior to transitions happened about 6:05. The change in the tail, so you can see the change in the turbulence level occurs in the tail, and so that's more obvious, I think, in channels 1 and 2. You start to see it first. But then this formation of a very narrow distribution, and so a great deal of turbulent suppression, strongest in channels 4 and 5, which is where the well begins to form. So these outer channels remain quite broad. Okay, sorry, it was stuck for a minute. And so what I've plotted here are these are PDFs of the perpendicular velocity. So some observation, and here's the radial profiles of the perpendicular velocity. So again, we're going from channels 1 through to channel 6, which is channel 1 is here, close to the scrape-off layer. The separatrix channel 6 is in the core. So some observations that the mean obviously shifts from positive to negative and going from L mode to H mode. Significant broadening of the distribution, so going from purple to orange, happens at the edgemost channels. Change in the perpendicular velocity is first seen in the edgemost channel. So we see it starting close to the scrape-off layer. So if I can guide your eye here, so I'm going from purple. So this this light purple profile first shows that change. You can see that the large change perpendicular velocity happens here. So this is prior to the formation of the well. It is pretty much at the formation of the ETB. So it's where this D alpha signal drops. And then you can see that the ER well, the V perp well starts to form, and it progresses as we go from channel 1, 2, 3, 4, 5, and then that's kind of well into the H mode, and we have this deep V perp well. So you can see the progression of it spatially from the scrape-off layer. So the key point here is that the what we think of as zonal flows are sufficient to trigger the ETB here. I mean, that's clear evidence of it. This is well before formation of the ER well. So the zonal flows themselves are sufficient to trigger the ETB. We see that a few milliseconds before. So we plotted these. So here we have the D alpha signal again, channels 1 through 6. We have the mean relative density fluctuation. So this actually gives you the turbulence level. And then the standard deviation of the PDS are given by this, not a true error, of the of this shaded region. So you can see the width of the PDS in the L mode-like phase, and then this narrowing of the PDS in the H mode-like phase, and this is consistent across. You can see the peaking in the mean consistently before the green vertical indicates where the D alpha drops. So again, it's a nice confirmation of the suppression of the turbulence begins, and the drop in the D alpha is a consequence of the ETB formation. And this is important because I think for years we took the drop of the alpha as the formation of the transport barrier, and we have confirmation that it begins before. It's a consequence of, it's an important marker as a consequence of the ETB formation. And the red lines here show you the back transition. So the ETB degrades, and then we go back to the L mode-like phase. So when we consider that flow diagram that I showed you before, the predator-prey model, we would expect the mean flow velocity to follow the suppression of the turbulence. And this is what we see. So you can see it here, this kind of a little bit in the edgemost channel. So that peaking, negative peaking of the velocity happens after the peak turbulence. And then that becomes, sorry, that becomes more significant in the region where the ER well forms. So you can see this very beautiful peaked velocity time trace here. So the phase difference between them is important. I think this gives us important information on the causality, which has kind of been an ongoing question. And then finally here we have the skewness of the relative density fluctuations and the skewness of the perpendicular velocity. We certainly see peaking in the skewness of the relative density fluctuation at the transport barrier change. For some of them, excuse me, it's pretty much at the transport barrier change. No conclusion from the skewness of perpendicular velocity. And as you could see, there's quite, dare I say, Gaussian structure. Okay, and so we've looked at similar, we've looked at the back transition. So here we're going from the yellow to the blue now. So from the H mode-like phase through to the L mode-like phase to see if the process was similar, their differences. For the relative density fluctuations, it's kind of a similar process. There weren't any notable differences here when we look at the PDFs. For the edgemost ones, you can see perhaps that this is more of a gentle progression of the drop, the increase in the turbulence, sorry. So you can see that kind of gradually for these edgemost channels. And then it's much sharper, I think, for the ones in the ER well region here, these channels. What we found interesting was that for the VPERP measurements, this I'm going to try and show you here. What we observe is that the change in the VPERP profile also starts at the edge. So it also starts in the edgemost channel. So you can see for this yellow profiles that the VPERP well remains intact, and the changes that we start to see, you can see this progressive change happens in the edgemost channel for VPERP. So indication that the erosion of the EV begins through changes in perpendicular velocity from the scrape-off layer inwards. And then you can see the gradual formation of this L-mode-like profiles.
Did you investigate hysteresis? Subject?
Not yet. It's a good point, Pat. So, okay, I'm really, how much time? I might skip this.
Already over time.
Okay. If you're interested in information geometry, come and speak to me afterwards. But basically, we've analyzed these results using information geometry to quantify. So it's very nice to look at the PDFs and to be able to track how they're changing. But we really want to be able to quantify that. So this is a method that we use to overlay a PDF with its adjacent one in time. So it's a future PDF and quantify how much that is changing. And so two metrics. One is a rate at which the PDF is changing, and one is an information length, which is giving you a dimensionless. It's a way to think about the changes in the statistical state. So the longer the information length, the greater number of statistical state changes that the system has. So very quickly, we find information rate peaks at both the forward and the back transitions. So here we have the green and the red consistently across all channels. Less consistent and very mixed picture for the perpendicular velocity. We see those peaks for this system consistently for the forward transition and a not so clear picture for the back process. And just to show you, we've analysed it across all cycles. So that's what I'm basing this on. It's not just a couple of cycles. So we can firmly say that the information length reveals very interesting separation in statistical space of the regions in which we're measuring, and these do not match up. So for this is the information length in the perpendicular, in the relative density fluctuations, and here we have it in the perpendicular velocity. They're kind of inverted, but I won't go into it because I can see that I need to go. So main conclusions. The results, these are the first results of the DBS analysis for the L to H transition dithering phase on MAST-U. We're very confident in these results and very happy to be able to present them. We see the most significant suppression in the region of PERP well formation, and those have the largest changes in the skewness and the mean value. The perpendicular moves from positive to negative, from L mode-like to H mode-like. And the changes in the VPERP happen from the edge. That's really the key point, from the scraper layer moving inwards. The zonal flows are sufficient to trigger the ETB formation. The mean flow plasma sheared region follows on from that and probably suppresses the turbulence further, allowing you to go deeper into the H mode. But we're concerned with the triggering mechanism. So I think we're quite confident with that from these results. And then some interesting results from statistical analysis, which I can speak to you about later. Sorry to go over.